Hello everyone and welcome back. Today we are going to be talking about trees. Now what is a tree? A tree is just a simple data structure whereby you have a head node or a parent node, and then this parent node points to other child nodes. Now these child nodes can be many. It can point to this child node, it can let's say point to this child node, and it can also point to this child node. There also can be another child node here. It can also point, let me first escape that, and it can also point to this child node. Now, it doesn't necessarily have to be too many child nodes that it points to. So usually when we are talking about a binary tree, we talk about, a tree, not a binary tree. Usually when talking about a tree, we talk about a binary tree. So a binary tree is whereby you have a parent node, and then the parent node has two child nodes. Then the child nodes become parents and they have two child nodes, or one child node. But it can only have not more than two. It cannot have not more than two child nodes. So usually when we're talking about a tree, we usually talk about a binary tree. But usually binary trees are usually used in binary search trees. But now how do these binary trees work? Let's imagine we had this tree. Let's put here, let me put another node maybe we wanted to add. Let me put another node here, and this node maybe should have 11 in it. Let's use another color. It should have 11. Now, the way trees work are like this. If the node you are trying to add is greater, if the node you are trying to first escape this, let me reduce this to that, escape. Let me come here, then let me highlight it small like this. So if the node which you are trying to add is greater than the parent node, it goes to the right. If it is less than the parent node, it goes to the left. So when it comes that you want to add a new node to the binary tree, we want to add 11, it will come here to the top, it will check 10. Now 10 is greater than what? It's greater than 11. 11 is greater than 10. It means that it will go to the right side. Here, 11 is less than 20. It will go to the left side. Then here, 11 is less than 15. It will go to the left side. Now 11 is greater than, 11 is less than 13. So it will also go to the left side. So at the end, this 11 will be on the left side of 13. That is if we are adding it to the binary tree. Now the good advantage of binary trees is that they're fast in searching. So when you're carrying out searches, they're incredibly fast. So now there are two types of binary trees. There can be a balanced and unbalanced. Now a balanced comes by whereby when you add, like if we add 2 as our parent node, it will have 2 child nodes. That will come in the case only when the nodes that you are adding, the first 2 nodes that you add, have to be less than and greater than the parent node. If they are not, you will have this unbalanced case whereby if I have 1 as my parent node, then I add the next node I want to add is 2, it will go here to the left. The next node that I want to add is 3, it will also go here. It will also go here to the right, like that. Meaning that this left side of the binary tree will not have been satisfied. But there are usually algorithms that are built in most binary search tree modules that take care of this problem. So now, if we are searching through a binary tree, there are 3 ways to search through a binary tree. We can have auto traverse. We can have the in-order traversal. We can have the post-order traversal, and then we can have the pre-order traversal. So now, how does a pre-order traversal work? In the pre-order traversal, we first print B, then we print A, then we print C. So in the pre-order traversal, it will be B, A, then C. Now in the in-order traversal, we shall first print A, then we shall print B, then we shall print C. So you will have the left node first, you print the parent node, then you print the right node. Now in the post order traversal, we shall first print the left node, the right node, then the parent node. That is how the post order traversal would work. But now, how do we implement a binary tree? So now we are going to start to implement a binary tree. Now, to understand how to implement a binary tree, you should also understand recursion. If you don't understand recursion, you may not be able to understand how this binary tree I'm going to implement it. And the language of my choice, which I'm going to use to implement this binary tree, is Python. So what you can do, you can open up your favorite text editor. Then, after opening up your favorite text editor, you can save it as, let me say, tree. I'm going to call it trees.py. I'm going to save it. So after saving my trees.py, I'm going to start off with my first class. Now the class which I'm going to define first is the node. So what I'm meaning by the node, I have to define these nodes here. These nodes here, these nodes. I have to define what they are. So let me go back here. So let me see. Let me go back here. So I'll first define my node. Now I will initialize my node class in it. I'll initialize my node class in it. It will take in self and then data, because each node has to carry some data. So I will have self.data will equal to data. Again, the node has to point to a left node. So I'll have self.left will equal to initial and none. Again, it has to point to a right node. Right will equal to none initially. So that will be my node class. Then I can now define my binary tree. So my binary tree. Now in my binary tree, in this case the way I've decided to implement it, the binary tree class will be able to keep track of the head. It should be able to keep track of the head. So I'll define myself and then data. So when you make the binary tree class at first, when you create a new object of it, you need to pass in your head data. So this head data, I will get a variable called head, and then the data which you passed in the binary tree object, I'm going to make it into a node and store it in the head variable. So this binary tree object is going to keep track of the head. But there are many ways you could implement it. You could not keep track of the head, and you would keep track of another thing if you would like. But there are many ways to implement it, as long as you have understood the core ideas behind it. So then I'm going to have my different functions. I'm going to have an insert function, which will help me to insert information. It will help me to insert information into the tree. Then I'm going to have another function, contains. It will check if the tree contains some certain data. So I'm going to say contains self pass. Then I'm going to have another function called print in order. So print in order. Now this function print in order will be able to traverse through the binary tree and print the functions in a predefined traversal, either in order traversal or pre-order traversal or post-order traversal. It does not matter. The core idea will be the same. So I'll say print in order. So in this case, I think I'm going to use the in order traversal to demonstrate this. So print in order. Print in order. So print in order will take in self, then pass. Now I have to go on to define these functions. So let's start with the insert function. So we would like to insert a what? Insert a function. Insert some new data into the binary tree. So what will this insert function receive? It will receive data. Then it will receive a node equal to none. Now the reason for this node that it is going to receive, it's going to help me in the recursion. Remember I said it's the way you implement a binary tree, you need to use recursion to implement it. Now later on, you're going to see the use of that node, which I've set as equal to none. So initially, when I want to insert data, I'll first check if the node is equal to none, meaning that if that node has no node has been passed into the insert function, then it means that I am in the first loop, should I say, my first recursion loop, something like that. So my node will equal to self.head. So that I will set my node to equal to self.head. Then I'm going to check if data, right, is less than or equal to node.data, meaning that if the data, like the data that I've passed, the data that I've put here, this example, I have put the data that I have passed, it's checking on this node now. If the data is less than this node, it has to put it to the left. If the data is greater than this node, it has to put it to the right. So that is the basic idea that that's the basic idea that I'm going for. So if the data is less than the node.data, what I'm going to check if the node.left is equal to none, meaning that if there is no left node, if the node.data is equal to none, then I'm going to select my node.left equal to node, then I'm going to pass in my data. Then after that, I can just return and end the function. I've already put the data into the tree. Else, what if my node.left is not equal to none? There is a left node. What I'm going to do, I'm going to say self.insert. That's where the recursion comes in. The function is going to call itself. It's going to pass data, and this time the node that it's going to pass is now not the head. The node we shall now be checking will be node.left. So, if you understand recursion, you should be able to understand how this is going to work. Now, we're going to go else if the data is greater than or equal to, if it is greater than or equal to node.data, it's greater than or equal to node.data, what we're going to do, we're going to check if the node.right is equal to none. If the node.right is equal to none, then my node.right, meaning that if there is no right node, then I'm going to set my right node to equal to the data that I have passed. Then I'm going to return, meaning that I'm going to end the function or return. Else, if there is a right node, what I'm going to do, the function is going to call itself, insert, and I'm going to pass in the data, and then the node that now we are trying to check will now be the right node, node.right. So that is the end of the insert function. That's how we insert data into the binary tree. So in this case, we have used recursion to do this. Now, what if we want to check if the tree contains some data? So first, we shall pass in the data that we want it to contain, and since now in this case we are going to use recursion, so I'm going to select my node initially equal to none. So first delete this pass. Let my node initially equal to none. So now I want to check if my node is equal to none, means that I am in the first recursion, which implies that my node should equal to self.head. Then I'm going to check if my data is equal to node.data, then I'm going to return true, meaning that the data exists. If it is the node, if the data which I want to check that the tree contains is equal to the data of this node, this initial node, which is the head node right now, but in the next cases it will be other nodes, then it means that I just return true that the data exists. Or if my node.left is not equal to none, meaning that if the left node is not equal to none, then I'm going to check if my node.left.data is equal to the data that I've passed, then I'm going to return that the data that I'm checking is there, so I'm going to return true. Then else, what if the data is not on that, is not on the left, that left node? Then what I'm going to do, I'm going to recall, the function is going to call itself. Self dot contains, then I'm going to pass in my data, and then I'm going to pass in my left node, node dot left. Then from there, what if now the left node is not also equal to none? Else if node dot right is not equal to none, node dot left is not equal to none, then I'm going to check if my node dot right dot data is equal to data. Then I'm going to return that yes, that data exists. Else if it's not the right node, then what I'm going to do, I'm going to say self dot contains, then I'm going to pass in the data, then I'm going to pass in the node, that's called, the function will call itself, and I'm going to pass in the node dot right. Now in this case here, we can do a simple modification here. Instead of each recursion we check this node, we check if the data is equal to true. What we are going to do, if the node is equal to none here, then what we are going to do, we are going to check if the data dot node is equal to the data, meaning that only, in this case we are only checking for the head node, then return true, because here in this case we shall check the data of the left node. So then when we pass in the left node and the function is repeating itself, we don't need to check again if the data of the left node is equal to the data that we want to check. So in this case we can make that small modification there. So that is how you check if the binary tree contains some information. So now we are going to use print in order. Initially, because remember we are doing recursion here, we can pass in a node equal to none. Then we are going to check if the node is equal to none. It means that we are in our initial recursion. So our node will equal to self.head. Self.head. Then we are going to check if our node dot left is not equal to none, meaning that if the left node is not equal to none, what shall we do? We shall just, the function will recall itself. Print in order our node dot left. Then after that, we are going to print our node dot data. So if you're not understanding, I'm going to try to explain this, what this means. Now if our node dot right is not equal to none, what we're going to do, the function is going to recall itself. Then we shall print in order node dot right. We shall pass in that. So now what we're going to do is let's try to explain it. So if, for example, we have our 10. Now the initial code shows that let's see, the initial code we're going to talk about is this here. If node dot left is not equal to none, call yourself. So if the left node, this left node is not equal to none, the function will call itself. Then again it will check if the left node is not equal to none, then it will come here again. If the left node is not equal to none, then it will come here. Then if the left node is equal to none, so in this case it will reach until the last left node here. So if it reaches the last left node there, meaning that now our left node is actually equal to none, then it will come here to print node.data. So what it will do, it will start, let me see, what it will do, it has reached here the last, and then the left node is equal to none. So what it will start, it will print out 1, then it will print out 3, then it will print out 5, then what? It will print out 1, then it will print out 1, then it will print out 3. Then our right node will be called and print not fall like that, then it will go backwards until it has printed everything we want. So it will print like going backwards. So in this case, let's say 10, we have 10, then we have 5, let's pick out that small portion, then we have 20. So what it will do, to check if our left node is, 10 will be passed, which is the head node. It will check if our left node is not equal to none, so it's not equal to none, so it will call itself. Itself will check if the left node is equal to none. It will find out that the left node is equal to none. After finding that the left node is equal to none, then the next line in the code will be executed, and the next line in the code is this print node.data. So when my next line in the node is executed, it will print 5, right? Then after printing 5, it will come back to the previous one. Remember, this one here ended on self-calling this one. Since this one has already been executed, it will come back to this one, and then it will print 10. Then it will check if our right node is not equal to none. It will come back here. Our right node is not equal to none. After checking that our right code is not equal to none, then it will print 20. So that's how it works. That's how usually the binary traversal works. So what you could do this is now an in-order traversal. If you wanted, like, for example, a pre-order traversal, what you do, you would just change the position of this print. You may put the print here, and then this one would come the next down, and this one will come the next down. So, like, for example, our pre-order traversal goes as it will go as head node. It will go as head node, left, then right. Head, left, then right. So then meaning that you would change this and then bring it. You would bring it pretty much here. So it will go head, left, then right. In order traversal will be left, then it will be head, then it will be right at the end. That's how you'd implement an in-order traversal. If you wanted a post-order traversal, then this print function would be put here for a post-order traversal. So that's how you implement a binary, usually a binary tree, which is mainly a binary search tree. Thank you for watching. If you enjoyed, you can leave a like on the video and subscribe to the channel.